So this is one of the first hard problems that I'm going to do on this channel. So I hope it goes well, and I hope this is going to be helpful for most of the people watching this video. So let's read the problem description. Given n non-negative integers representing the histogram's bar height, where the width of each bar is 1, find the area of the largest rectangle in the histogram. So let's look at one of the examples. We have a histogram here with 6 bars, and they're saying that the optimal answer in this case is a rectangle with width 2 and a height of 5, which yields an area of 10. So the input is going to be represented with an array like this, and the ideal answer your algorithm should return is 10. The rest of the examples are helpful for showing you what kinds of rectangles are valid, and just gives you more examples. But I think that the problem is pretty straightforward just from the problem description. Now, let's take a closer look at how we're going to solve this problem. So I've reproduced the histogram here, and we're going to look at what exactly we need to do to find the optimal answer. First, we have to consider the main idea behind the algorithm we're going to use. We know that constructing a rectangle involves 2 parts. We have to specify the height, and we have to specify the width. Now, we can fix the height and then try to maximize the width in order to maximize the area. But the problem is, how do we figure out the width of a rectangle? Well, width can simply be determined by the left and right boundaries of that rectangle. So let's say that we're constructing a rectangle of height 6. And we know that that rectangle has to be bounded on the left and right hand sides. So this rectangle cannot expand any more to the right because there's a drop here. It certainly wouldn't be a valid rectangle, and it would violate the constraints of the problem. So the right boundary is 2 here, and the left boundary is 5, because again, there's a drop here. We can't extend the rectangle anymore to the left. So given that we can figure out the left and right boundaries, we can actually calculate the width of the rectangle. And we just fix the height to be 6 for this example. Since we know the height and the width, we can calculate the area. So this is going to be the main idea behind our algorithm. And our algorithm is going to be something like the following. We're going to scan through each bar of this histogram and set the value of that bar as the height of our rectangle. And then we're going to find its left and right boundaries and use that to calculate the width. Once we have both the height and the width, we can calculate the area. Once we calculate the area, we can just update a current maximum area variable to see if it improves on our answer so far. Now, how are we actually going to find these left and right boundaries? Well, the key here is to use a stack. This stack is basically going to keep track of the numbers in ascending order. How is this going to be helpful? Well, let's look back to our previous example. So we're constructing a rectangle here of height 6. And let's say we have a stack that keeps track of all the bars' values, all the values of the bars in the histogram in ascending order. So let's say we have 1, 5, and 6 in the stack right now. And 6 is at the top of the stack. Well, if we eventually walk to 2, we see that there's a drop here. 2 is less than 6. So we actually can't expand this rectangle any further to the right. We know that we've encountered a right boundary simply because 2 is less than whatever is at the top of the stack, which is 6. So we have a right boundary, But how do we get the left boundary? Since our stack is in ascending order, all we have to do is look at the element that comes before 6 in the stack, which should be 5. So we know that that's true as well, because we can't extend any more to the left for this rectangle, because 5 is not tall enough. So this stack is basically a data structure that we're going to use to make sure we can find the left and right endpoints of a rectangle very efficiently. Okay, so in order to better understand this algorithm, let's actually go through a concrete example. So first, let's scan through all the bars of this histogram. Notice that I've added fake indices here, -1 and 6. These do not appear in the original array. They only make it easier for us to program the solution to this problem. And I'll explain more about how they work later. But in the meanwhile, we should just focus on the first bar in this histogram. Now, we're going to follow 2 rules in this algorithm. First, we're going to pop while the heights of I is less than the heights of stack -1. What does that mean? It means that whatever the height of the current bar we are at is, if that is less than the height of the bar corresponding to the index that's at the top of the stack, if it's less than that number, then we should pop an element from the top of the stack. Else, we should push the current number we are at on to the stack. So it's going to be a little confusing here because we are actually pushing indices onto the stack. We're not actually pushing values. So I may mess up a little bit, and that may get confusing while I'm explaining this problem. But know that when we're actually implementing this, we're actually only going to be working with indices, because you can always recover the original value as long as you have the index. I think that's going to be more intuitive and more clear when I implement the code later anyways. So let's begin. We're going to start at the beginning of this histogram, and we're going to check, is the number we're at less than whatever is at the top of the stack? So this is index -1. Index -1 in Python means that we are going to go to the very end of the array. And notice I have this fake value added to our array, which basically is a bar of height -1. This is a fake value I added in order to make the problem easier to solve. So we're going to talk more about that later, but I chose -1 because it won't affect the final answer we get. A rectangle with height -1 is not going to be is never going to be an optimal solution. The lowest area we could get for a rectangle is 0. So it's not going to affect our final answer. That's why I chose -1. In any case, let's go back to our rule. We're going to check if 2 is less than -1. That's not true, so we're going to push. Okay, now let's move on to the next one. Is 1 less than whatever's at the top of the stack? Oh, excuse me, I made a mistake here. So we're only going to be pushing indices here. So, okay. Now, is 1 less than whatever's at the top of the stack? So this 0 is referring to index 0. We're comparing 1 to 2. Is 1 less than 2? Yes. So we're going to pop this, and that means that we're going to construct a rectangle of height 2. Here we go. Okay, so we're constructing a rectangle of height 2, and we know that the right boundary is wherever we just left off, which is index 1. The left boundary is whatever becomes before whatever comes before the element we just popped off the stack, which is -1. So the right boundary is 1, the left boundary is -1. Let's calculate the width. What we do is 1 minus -1 minus 1, which is 1. That's correct. And we have a height of 2. So the maximum area is 2. So just to clarify, we initialize maximum area to 0. But since the area of the rectangle we just calculated is bigger than 0, we should update that variable to say 2 now, because that's the maximum area we found so far. Okay, now we finished that step, and we're going to resume where we left off. So we were at 1 before. We're going to see, is 1 less than whatever is at the top of the stack? So this is an index. Remember, in Python, -1 index means we're looking at the very end. So we're comparing these two. Is 1 less than -1? It's not. So we should push 1 onto the stack. Okay, now again, we're going to ask ourselves the same question. Is 5 less than 1? It's not. So we're not actually going to push 5, we're going to push the index, right? I always mess this up, but you have to remember this. This is important. We're going to push the index of that bar. Okay, so is 6 less than 5? It's not. So we're going to push the index onto the stack. Okay, so now we're going to ask ourselves the same question. Is 2 less than 6? That is true. So we're going to start popping now. So we're going to pop 3, which means we construct a rectangle of height 6. And then we know our right boundary is wherever we just left off, which is index 4. And our left boundary is what comes before what we just popped off the stack, which is index 2, which is 5. So rectangle of height 6 and width 1. What's the area there? The area is 6. That actually is an improvement, so we update our maximum area. Okay. Now we're going to check the rules once again. We're going to check if 2 is less than 5. It is, so we're going to continue popping. Remember, pop while heights I is less than heights of stack minus 1. So we're going to pop 2, which means we're constructing a rectangle of height 5. And our right boundary is still going to be 2, because that's where we left off. And our left boundary is whatever came before 5, whatever came before the thing we just popped off the stack, which is index 1. So now it's going to be a rectangle like this. It's going to have height 5 and width 2. And let's just show one more width calculation. That's 4 minus 1 minus 1, which is 2. So that's 5 times 2 is 10, which is greater than 6, so we update maximum area. Now we go back to our rules. Is 2 less than 1? That is a no. Therefore, we're going to start pushing the index associated with this bar. So we're going to push a 4 on there. And then we're going to move on. We're going to go back to the rules again. Is 3 less than 2? No. So we're going to push. Now, Remember this fake value I added to the array? We still have to consider it because it's still part of our array. So, is -1 less than 3? It is. So we're going to start popping again. What does that mean? We're going to look at index 5. We're going to construct a rectangle of height 3. Just give me a moment here to get that squared away. And then we know that we just stopped at index 6. So that's our right boundary. And our left boundary is whatever came before us in the stack. So that's index 4. That should be a width of 1 and a height of 3, which is an area of 3 that doesn't really improve on our max area. So we're going to ignore it. Then we're going to go back to our rules. Is -1 less than 2? It is. So here's what we're going to do. We're going to pop, construct a rectangle at that index with height 2, and then the right boundary is going to stay the same because that's where we left off. And that's where we saw the drop, right? And then the left boundary is whatever came before us in the stack. That's index 1. So now we have a rectangle of height 2 and width 4. That's an area of 8, which still isn't better than our maximum area. So we ignore it. Okay, now we go back to the rules again. Is -1 less than 1? Yes. So we're going to pop it off. We're going to construct a rectangle with height 1. Let's see. And then the right boundary is still -1 because still that's where we left off. And the left boundary is whatever came before us in the stack, which is -1, this fake index I added. So now we have a height 1 rectangle with a width of 6. That's an area of 6, which doesn't increase our maximum area. So we ignore it. Okay, now we go back to our rules. Is -1 less than -1, right? Because heights I is -1 here, and heights stack -1 is referring to this same -1. Because remember, in Python, -1 is the last element in the array. So that's not true. So then we're going to push. Okay, so then we're going to move on to the next bar, but there is no next bar. So that means we're at the end of our for loop and we terminate. What do we return? We return maximum area, which is 10. Is that the correct answer? Well, given this array, which is what I reproduced in the drawing, 10 is in fact the correct answer. So, overall, that seems like a very complicated algorithm because there's just so many moving parts. But you just have to understand the main idea, which is that we're just trying to find left and right boundaries for rectangles and keeping track of a running maximum area variable. So let's go through the code. We're going to start with declaring our variables first. Remember, we had a maximum area. We're going to initialize that to 0. And then we're going to basically put our fake numbers in there. Remember, I had like a fake -1 bar in there. That is this one. And we're going to have a stack, right? So we're going to declare all those variables first, and then we're going to write our for loop. For I in range, length of heights, we're going to start doing some logic here. So remember, I wrote that while heights I is less than height stack minus 1, we're going to pop. So I'm going to write the same thing. While heights I is less than heights stack minus 1. We're going to say that the height of our constructed rectangle is going to be the heights of stack minus 1. Or sorry, we actually have to pop from the stack. Okay, so we're going to construct a rectangle with that height. And then we have to calculate the width. This is where we find our left and right boundaries. We're going to do wherever we left off, which is I, minus whatever came before us in the stack. So that's going to be stack negative 1 minus 1. So let me just make sure that that makes sense. If we were looking at the rectangle that has a height 6, and we're looking at how to calculate the width from the left and right boundaries, then what we're doing is the following. We're doing I minus stack negative 1 minus 1. So that is 4 minus 2 minus 1, which is 1. That's correct. This rectangle does indeed have width 1. So I is wherever you left off. Stack negative 1 is what came before you in the stack. And you do a minus 1 to compensate for the larger interval here. Basically just to get the correct answer in the end. Okay, so we've calculated the height and the width, and we can calculate the area now. So what we do is update maximum area when applicable. Right? That should be pretty straightforward. Okay, and then remember, if this while condition isn't true, we start pushing, right? So in Python, we will write that as this. And remember, only put indices onto the stack. Okay, so at the end, you can just return a maximum area. Let's see how this code runs. While heights I'm sorry. So the reason why we got an error here is because my stack didn't initially include a negative 1. And as you see in my example, it has to include a negative 1. Why? Because if the stack is initially empty, then I'm going to I'm basically accessing negative 1 index from an empty stack, which is going to they're going to yell at me for that. So we're going to say that the stack begins with a default element of negative 1. Okay, so let's see if it actually solves the problem. Okay, so we were able to solve this problem. Let's go through the time complexity really quickly. So the time complexity is simply linear time. And this is a little tricky to see because we have 2 loops in the code. But essentially, we're only considering each bar once. We're pushing and popping each bar. And there are n bars, so it's linear time. Pushing and popping is really fast. They're both constant time. So that's the time complexity. And in terms of space complexity, we only need the stack, right? And again, we're only pushing and popping each bar once. And the biggest this stack could get is basically the entire histogram, which is n bars. So the space complexity is also a big O of n. Okay, well, I hope this explanation helped you. If you like this video, please like, comment, and subscribe. Thank you.